Hi, everybody. This week we're looking at our chapter on sampling. Look, I couldn't see the title. Chapter 7, Chapter 7 on sampling, estimating the frequency of behaviors and beliefs. So we'll talk a little bit about generalizability, populations versus samples. How do we know when we have a good sample, when it's biased? How can we obtain a representative one? Settling for an unrepresentative sample, worst case if we need to, and then a little bit more about external validity. So how do we get our sample that we're going to be using for our experiment or for our research, and some of the different implications of that. So first thing to mention here, when we're talking about populations and samples, we're looking at a concept that is very kind of central to external validity, which we mentioned previously, and that's something called generalizability. Does the sample that we're using represent the population? So for example, if you see a claim, something like 3 in 4 women worldwide rate their lives as struggling or suffering, where did they get those women, right? 3 of 4 women, right? So where did they gather that sample? Where is that data coming from? I love this, right? I have a positive result, sample size 1, right? How many people did they ask? Was it random? Was it chosen on purpose, right? Was it a convenience sample? Those are all questions that we need to ask if we want to know if the sample is representative of more than the people that they asked in the survey or in the experiment. So to define those terms a little bit more, population, sample, census, so let's look at those terms a little bit. The population is the entire set of people or things or in which you are interested. So the entire group, right? So if we were going with that last example, the population would be every person who identifies as a woman in the world, every female in the world. That would be our population. It's the entire group of everything that you're interested in studying, every single individual. The sample is a smaller set of people or things taken from the population. So rather than asking every single woman in every single country, let's say we ask 1,000 women from 160 different countries, right? So we take a smaller sample or just a little taste of the population at whole. A census would be every single member of the population, right? So if we literally asked every person in the world who identifies as a woman. Now, sometimes a census is possible, but for the most part, it is not possible to ask every single person of a population, nor is it necessary. We actually don't need to gather information from the entire population if we take a good sample. So if we do our sampling methods correctly, we can take just a smaller little subset and have that be where we can still draw accurate conclusions and still have that data be generalizable to the larger population at hand. So when we're trying to make inferences from a sample to a population, it's really important to think about how the sample was selected. So if we want to be able to take a smaller group of people and then from those people generalize to a larger group and to the entire population, we have to make sure that we select a sample in a very unbiased way. An unbiased sample, another way for coining that would be a representative sample, would mean that all members of the population have an equal probability of being included. Everybody has an equal chance or probability, and we're going to kind of randomly select through a bunch of different methods that we can use to get that representative sample. A biased sample is unrepresentative. Not all members have an equal probability. We're doing something that makes it biased. So a biased sample example, recruiting people sitting in the front row at the Texas Democratic Convention. Only the people in the front row. I'm going to pick just from you, totally biased. Not everyone has an equal chance. The people in the second row, third row, and beyond don't have any chance of being included. An unbiased sampling technique, I'm going to obtain a list of all registered Texas Democrats from public records and I'm going to call a sample of them through some kind of randomized digit dialing. So we're taking everybody and everybody has an equal chance of participation or being included in the study. There are definitely ways to get a biased sample. Remember, we don't want a biased sample. Biased or unrepresentative samples are not what we're looking for. But one of the most common ways that people end up with a biased sample is they do something called convenient sampling. They sample only those who are easy to get a hold of, that you have easy access to, or are easy to contact. So let's say I wanted to do an experiment and I only ask all of you. I'm like, all right, great. I've got a research methods class. Perfect. I've got a nice little sample right here that I can use. That would be a convenient sampling. I'm using those of you who are easy to get a hold of, easy to contact. You're available to me right now, but it's going to be biased. Not everybody has an equal chance of being included. It's only what is convenient. That is a very common way that we get biased samples. Another one that we might do is something called self-selection, only sampling those who volunteered. Now, sometimes it gets tricky to get people to volunteer for research and for experiments. There's a lot of reasons why someone might not. But if we only sample people who are eager to participate or who volunteer, we're going to end up with a bias, right? So only sampling those who volunteer who are willing to participate will give us a self-selection bias. That's another way that we can get very unrepresentative data. If we want to try to obtain a representative sample, there are a bunch of different probability sampling techniques. Another way of saying probability sampling is to say random sampling. So the essence of this is that we want to make sure that every member of a population has of interest, whatever it is we're studying, has an equal chance of being selected for a sample. So let's say that I want to know something about Moore Park College students. I want to know what is the average stress level of the Moore Park College student on a scale of 1 to 10. Right? If I wanted to know that, in order to gain a random sample of people from Moore Park College, I would have to make sure everyone has an equal chance. Now, if I wanted to do a non-probability sample, I could just easily ask all of you, be like, hey, what do you think on scale 1 to 10? But that might not generalize to the rest of the campus. I want to make sure that everyone in every different class, every different student, different times of day that you're in classes has an equal chance of being selected. And that's what's going to give us the most representative sample. And we can do that again through probability or random sampling techniques. And there are a bunch of them right here that we'll talk about over the next couple of slides. The probably easiest way to do this is to do what's called simple random sampling. Maybe we assign a number to each member of the population, and then we use a table of random numbers to select a sample. That's a very, very common method. Let's say I'm going to pick a number at random, 9. Every 9th number on your student number list of all the students who go to Moore Park College will be contacted for my experiment or for my survey. Right? We're going to use some kind of numbering to create like a random sample that we're selecting. We can also do something called a cluster sample. Clusters of participants within the population of interest are randomly selected, and then all individuals in each selected cluster are used. Right? And depending on the technique and the number of people that you need and what you're studying, there are going to be different ones of these methods that are more appropriate. In general, if you can do a simple random sampling, great, but then we have these other methods as options as well. So let's say, for example, my population of interest is all California community college students. If I were to do cluster sampling, there are 114 colleges in the California community college system. I would randomly select 50 clusters, 50 colleges. Each college could be considered a cluster. And then of those 50, I would ask every single student that goes to those colleges. We can still trim that down a little bit because that would still be an incredible number of people, but that would be an example of a cluster, right? If we wanted all community college students in California, we randomly select 50 clusters or 50 colleges, and of those 50, we ask every single student who goes there. We can also do something called a multi-stage sampling technique. This is another way to get a representative or probability random sample. 2 random samples are collected. Stage 1, the random sample of clusters is selected from the population of interest. And then in stage 2, we select a random sample of people from those clusters. So we're taking the cluster sample idea and we're trimming it down even more. So same idea, if we had California community college students, we randomly select 50 clusters. And then at each one of those 50 colleges, we ask 200 people that we selected at random. Imagine how many less people that would be than this previous example. Rather than asking all like 10,000 students who go to that college, maybe it's 200 randomly selected from each one. So we can still get a really good sample, and it's still very random and representative, but we've asked considerably less people in the process. We can also do something called a stratified random sampling. The researchers select specific demographic categories, such as ethnicity or gender, and then randomly selects individuals from each of the categories. So again, going with the same example, California Community College students, but now we want first-time students. Let's say that we want to know the first-time student information. We want to know the proportion of ages, which we have right here. In a sample of at least 1,000 students, we want to include 60, at least 50 plus students. So we want to at least have 60 people in the 50 and plus category. We're still selecting them at random, but we're targeting a specific demographic category. We're stratifying the data a little bit more and then randomly selecting within that stratified information. We can also do something called oversampling, a variation of the stratified random sampling I just mentioned, in which a researcher overrepresents one or more groups. So for example, the population of interest, again, California Community College first-time students. We know the different proportions of ages. We have broken that down into different categories. And in our sample of 1,000, we include at least 150 plus aged students. We're still selecting them at random, and we're going to adjust our final results so that oversamplified group is weighted to the actual proportion. But if we're really interested in that group of 50 and over students, we want to make sure that we get enough data from that category that we can actually get the results that we're looking for. And then we might have to adjust the data and weight it later to make sure that it all kind of comes out equally in the end. We can also use something called systematic sampling. Using a random number table, we select two numbers. So for example, 5 and 3. And then we start with the 5th person and choose every 3rd person until the sample reaches its desired size. This is kind of combining techniques in a way, right? But systematic sampling, right? So they have this example here. We start with this house and then we're going to choose every 3rd house from there. So it's random, but we have like a very systematic way that we're trying to get that information and decide who's participating. So each technique involves some element of randomness to ensure an equal chance of being selected. When everybody has an equal chance, the population is much more represented, right? And it is a little bit less biased, and we can call it a probability or a random sample. That's really, really important for being able to generalize information. When a sample is biased, the information that we get from it may or may not be all that meaningful. So very important to have that element of randomness to help us avoid bias. Now, you may have heard the term random assignment, and these two get confused quite a bit. So I just wanted to take a second to clarify. Random sampling versus random assignment. Random sampling is what we've just been talking about, right? Where you want to make sure that you have a randomly selected group of people to get that probability sample. And when you select people randomly, it increases external validity because your information is generalizable to others. Random assignment is different. We talked about random assignment a little bit before, and we'll talk about it more again later. Random assignment refers to the use of chance procedures, usually in an experiment, to ensure that each participant has the same opportunity to be assigned to any given group. Study participants are randomly assigned to different groups, such as the experimental group or the treatment group. So say we have an experiment that we're doing where we talked about, for example, sleep deprivation on exam scores. And I have two conditions where one group is going to get a full night of sleep and one group is going to get interrupted sleep. I would want to randomly assign my participants to those two different conditions through some random procedure, maybe picking a number, drawing names out of a hat, or something like that, some kind of condition that way. And by doing random assignment, we increase internal validity. We're eliminating some of the confounds and we are controlling some of the elements of the experiment. So just something to differentiate. Random sampling has to do with how we gather our participants, and it's going to increase external validity. Random assignment is how we kind of put them into different groups and conditions within the experiment, and it's going to increase internal validity. Sometimes we have no choice but to settle for an unrepresentative sample. And so there are ways to get non-probability samples. And obviously these aren't ideal, but there are times where we have no choice. The only way that you can get information is to just take what you can get, or to take something that is that is not random. And so we talked about convenience sampling, that maybe you can only ask the people that are available to you. Another very common non-probability technique is something called purposive sampling. If you want to study certain kinds of people, so you only recruit those types of participants in some kind of non-random way. So for example, let's say that you want to study people who have Alzheimer's. So you put flyers up in different clinics and places that might have high levels of Alzheimer's patients, or people struggling with Alzheimer's. And you're just kind of taking what you can get. So you're purposefully calling people to try and get them to come in, people who have Alzheimer's. So if you have a flyer trying to maybe recruit participants of a certain group, that's more purposive sampling. It's very purposeful, trying to gather that certain population. Snowball sampling is when participants are asked to recommend others for the study. So let's say you have kind of a rare group of people that you're studying, or maybe a rare condition. So you're even, let's say with Alzheimer's, you're studying Alzheimer's. And so you ask people, oh, I'm sorry, hitting buttons, ask people who have Alzheimer's, do you know anyone else who's struggling with this that I can contact? And you're kind of snowballing away from that original contact point to get other people. Quota sampling is when you identify a target number and then you just fill it. So I need 500, and I'm just going to get 500 of whatever people that I can until I fill that, and I'm not going to worry about the randomness of it. And again, none of these are ideal, but there are times where you don't really have much of a choice. If you're trying to study a certain population, you might have to use one of these non-probability sampling techniques. Or if what you have available to you is incredibly limited, but it does affect the generalizability of your results. So if you use one of these methods, your results might not be quite as meaningful as if you had used a better one. Last slide here, what matters most, right? This is another thing that we kind of talk about a little bit. How many people do you need, right? How do we know how many people to ask as part of our sample? And there is a whole complicated statistical formula for calculating what's known as power, which we're not going to get into here. But a large sample isn't necessarily more representative than a smaller one. Sometimes less is more. The techniques that you use are more important than the sample size. And I know this is research methods, but if you ever take a human sexuality class, you would learn about Kinsey. And Kinsey is a very famous researcher who studied sexuality, and he had these incredibly large samples. He would ask everyone, I mean, just thousands upon thousands of people, but the techniques that he used were really not random at all. He would ask his students, whoever was convenient and available to him. He's been very heavily criticized over time for not having better sampling techniques. So it's more important to sample properly and randomly than it is to get an absolutely massive sample that was gathered through less statistically sound methods. So in general, better to worry about how than how many, as just kind of a general rule of thumb. So that is it for our chapter on sampling. Please get going on the other weekly materials. Make sure you do the discussion and the reading in the textbook as always. And I will see all of you next week for our next topic.